So today's lesson is going to be on vertical and horizontal asymptotes. So whenever we take a polynomial and divide it by another polynomial, we have a rational function. And we're going to get asymptotes in that case. And we're going to look at vertical and horizontal asymptotes, but we're also going to look at oblique asymptotes as well. So let's do a little investigation. Okay, if I take this function, 1 over x minus k, and I plug in different values for k, we can see what's going to happen here. So this is the function. And if I change k, you can see we get a different vertical asymptote. If k is 2, we get a vertical asymptote at 2. If k is 5, we get a vertical asymptote at 5. It's because in this function, if x and k are the same value, it becomes undefined at that point. Okay, we can look at another function like this one, x plus 3 over x minus k, and I'll change the value of k. So that's going to be the green one here. Right, so you can see what's happening. Okay, same thing as k increases, we're still going to get that vertical asymptote, like so. Then of course, right here, we don't get a vertical asymptote. However, if I go to that point, it is still undefined at -3. So to get a vertical asymptote, right, you do need the denominator to equal 0 so that your function is undefined, but also the numerator can't be 0 as well. If the numerator is also 0, you won't get an asymptote there, you'll just get the function undefined at that point. Right, and lastly, let's check this function down here. So that's our purple one. Okay. Now you can see that that function, you could factor the denominator, and since it's a quadratic, you can end up with 2 vertical asymptotes, as you can see there. All right, so those are the conditions you need to get a vertical asymptote. Okay. And let's take an example first. So let's say we have this function. There's x divided by x squared plus x over 2. You can find the vertical asymptotes just by solving the denominator when it equals 0. Right? Because when that function's undefined, that's when you'll have a vertical asymptote. So if you factor it, we get, in this case, x minus 2 and x equals 1. And those are both safe because if x is -2 or 1, the numerator is not also 0. Okay, now, with our asymptotes, we want to know whether or not our asymptotes are approaching infinity or negative infinity. So are they rising or are they falling? Right, that helps if we're going to graph something. So what we need to do then is we need to look at these 2 points, -2 and 1, and we can take a number, for example, as x approaches -2 from the left. I have to remember our limit notation here. As x approaches -2 from the left, is the function going to be positive or negative? And we're going to take a number a little bit smaller than -2, like -2.1. Right? If -2.1 is x, you can check in your function, and you'll end up with a negative value. So that means it's approaching negative infinity. So what this looks like here is here I have this dotted line is our vertical asymptote at -2, and from the left, we get a value that's getting quite negative, so it's going down to negative infinity there. If we take a number that's slightly to the right of -2, like -1.9, and test it, it turns out to be positive in our function. So at that point, our function's approaching, I just went past the line there, approaching positive infinity, like this. And we do the same thing for our other asymptote x equals 1. we try a number a little bit less, so coming from the left, so like 0.99. We test it in our function, turns out to be negative, so our function's approaching negative infinity. Similarly, test one a little bit greater than 1, like 1.01. It's positive, so we're approaching positive infinity. All right, now I'm going to show you how to find a horizontal asymptote. Now, there probably was a rule you learned in your previous course, but I'm going to show you where this rule actually comes from. So let's take a polynomial, like x squared plus 4x plus 1. And what we're going to do is we're going to factor out any factor that would make that first term in the bracket equal to 1. So if we do that, in this case, we want this first term to be 1, so I'm going to pull out an x squared. If I pull out an x squared, I'm going to get 1 plus 4 over x, right? Because if you multiplied 4 over x times x squared, you just get 4x, plus 1 over x squared. And the reason why this is going to be useful is because the limit as x approaches either positive or negative infinity of 1 over x is 0. So that means if we were to take the limit of this function, these values would be 0. Now in this case we still have x squared, so the limits doesn't exist, it blows up. But let's look at another example. Let's look at this one. Determine the value of the following limit. So we're doing infinite limits here. The limit as x approaches infinity of 2x minus 3 all over x plus 1. So what we're going to do for both numerator and denominator, we're going to pull out the highest factor to make the first term 1. So to do that, this is just going to equal the limit as x approaches infinity. So 2x, so we're going to pull out a 2x here. So we got 2x. And then we have 1 minus 3 over 2x for the numerator. On the denominator, we have an x here, so I'm going to pull out an x. And that's going to leave me with 1 plus 1 over x. Now you'll see right here, our x's will actually cancel. And if we apply this limit in the brackets, these limits here are both 0. So this limit as x approaches infinity reduces to 2. So what does that mean? It means as our value of x approaches either positive infinity or negative infinity, it approaches the value y equals 2. So y equals 2, in this case, is a horizontal asymptote. And that is going to be our strategy for finding horizontal asymptotes. And you'll always get a horizontal asymptote as long as the numerator is a power of the same degree or lower. So let's start with the first example then. This one says, determine the equations of any horizontal asymptotes of this function, and state whether the graph approaches those asymptotes from above or below. Okay, well, to find any horizontal asymptotes, we're going to find the limit as x approaches infinity for that function. So the limit as x approaches infinity for 3x plus 5 over 2x minus 1. So we're going to pull out the highest factor in each case. So this is going to be the limit as x approaches infinity. So here I'm going to pull out a 3x, which leaves me with 1 plus 5 over 3x in our numerator. And in the denominator, I'm going to pull out a 2x, which leaves me with 1 minus 1 over 2x. So as the limit approaches infinity, these terms here, the 5 over 3x and the 1 over 2x approach 0. These x's actually cancel, so we are left with 3 over 2. So we have a horizontal asymptote at y equals 1.5. So I have that drawn right over here. So there's our horizontal asymptote. Now we need to know whether or not the function approaches it from above or below. And we're going to need to know as that function goes to positive infinity and as that function goes to negative infinity. For positive infinity, just choose a big number. For example, what is the value of this function at 1,000? Well, 3 times 1,000 plus 5 gives us 3,005. All divided by, on the denominator, we'd have 1,999. And that value is greater than our asymptote 3 over 2. So if it's greater than the asymptote 3 over 2, it approaches from above. Right? So as the values of x get very, very big, it's above the asymptote. So it's coming from above to towards the asymptote. What about negative infinity? Well, just choose a number that's really, really, well, not small, but really, really large in the negative values. So negative 1,000. Okay, so you have negative 1,000. And we should get, actually, just realized that should be 30,005, and this should be like that. There we go. So negative 1,000, we get 2,995 all over and 1, where both cases are negative, and that is less than 3 over 2. So if that's less than 3 over 2, it means we are approaching that horizontal asymptote from below. Okay, so just make sure you get rid of those extra digits. I don't know why I thought I made a mistake when I didn't. So let's move on to the next example then. So this example says we have this function, and we want to determine all equations for all horizontal or vertical asymptotes and illustrate their behavior. So I've got it graphed here, so you can see this is going to be a lot. But that's okay. I'm just going to move over to the side here so we have some room. I'll just move right over, and I will rewrite the function here for us. So the function is 3x all divided by x squared minus x minus 6. All right, so first let's start with vertical asymptotes. So to find a vertical asymptote, we want to set the denominator equal to 0 and solve. So here we're going to have x squared minus x minus 6. Okay, we can factor that so that we have x minus 3 and x plus 2. And so now we know some values of x where it can make that denominator 0. X can either be 3 or x is negative 2. And that will not result in the numerator being 0. So that means we have these two vertical asymptotes at x is 3 and x is 2. So now we need to test whether or not these asymptotes are going to positive infinity or to negative infinity. Right? Are they going up at a point or down at a point? And from both sides, right? So first, let's try 3, our asymptote for 3. So as x approaches 3, and we'll start from the left, let's choose, you can choose a number very close to 3 from the left. So for example, 2.9. Okay, and if you sub that into the original function, you'll see that you get a negative number. So that means it approaches negative infinity from the left. If you try approaching 3 from the right, just pick a number that is slightly greater than 3, like 3.1 or 3.01, whatever. And you'll see you get a positive value in your function. You don't need to know whether or not it's what the exact value is. You just need to know whether it's positive or negative. And so if it's approaching 3 from the right, that means we are going towards positive infinity from the right. So if we look at the graph then, okay, here's our asymptote at 3, right here. And if we're approaching from the right, you can see, yep, we're going to positive infinity, so we're going to draw it like that. And from the left to negative infinity. We're not going to connect the graphs yet, as I will teach you more things tomorrow, like the second derivative test, to figure out what's going on in between and all of that. Okay, so for right now, we're just looking at those asymptotes and how they behave near those asymptotes. So we also need to figure out what's happening at this asymptote. I wrote 2, but it should be -2 here. There we go. So as x approaches -2, let's say from the left, let's choose a number slightly smaller than that, like -2.1. And if we check that, we realize it's less than 0. So from the left, it's approaching negative infinity. If we test it from the right, so -2 from the right, test a number a little bit to the right of -2, like -1.9. And we get a value that's greater than 0. So it's approaching positive infinity. So positive infinity from the right, negative infinity from the left. And we can see that in our graph. So from the right, positive infinity, and from the left, approaching negative infinity. Okay, so now let's test for horizontal asymptotes. Now a vertical asymptote approaches either positive or negative infinity at some value of x, where a horizontal asymptote, right, is going to go to an x value of positive or negative infinity at some value for y. So we're going to be testing the limit then of that function as x approaches infinity. And let's pull out a 3x on the numerator, which we don't have to do anything with that. And in the denominator, we're going to pull out an x squared, which will leave us with 1 minus 1 over x minus 6 over x squared. So as this approaches infinity, well, first we're going to get these canceling. This is going to be 0. This is going to be 0. And we're left with 3 over x. As x approaches infinity, 3 over x is also going to be 0. So we're left with this being 0. That means we have a horizontal asymptote at 0. Now we just need to know if our function is approaching this horizontal asymptote from above or below as it approaches positive or negative infinity. So test very large and very negatively large numbers, like 1,000. I mean, I've been doing 1,000, but if you have another large number you prefer, like 1,000,000, go right ahead. Doesn't matter. But if you test f at 1,000, you'll get a positive number. Therefore, it's approaching from above. And if you test f at, say, -1,000, you are going to get a negative number. Therefore, it's approaching from below. So if we go check out our graph here, okay, it's not dotted because it's right on the x-axis, but there is a horizontal asymptote right there. And you can see it's approaching positive infinity from above and negative infinity from below. All right, so in our last example, we are going to determine all asymptotes, but specifically, we have an oblique asymptote here. Now, we also have a vertical asymptote, because you can clearly see in the denominator, if x is -1, we're dividing by 0. So we do have a vertical asymptote at -1. But for this question, I want to focus on the oblique asymptote. So you'll get an oblique asymptote anytime the degree of your polynomial is greater in your numerator than in the denominator. So you can see in this case, in the numerator, we have a degree of 2. In the denominator, we have a degree of 1. Specifically, that degree is going to be 1 degree greater. If it's 1 degree greater, we're going to get this. I've graphed it for you already, but we have an asymptote, a linear asymptote that's on a diagonal. And that's going to have an equation. And we're going to figure out what that equation of that line is for that oblique asymptote. First, let me go down here. I'll rewrite the function. So we have f at x equals 2x squared plus 3x minus 1 all over x plus 1. So that was our function. Now what we could do is we could find the limit of that function as x approaches infinity. So essentially we're trying to test for a horizontal asymptote here. And if we do that, well, we will factor out the 2x squared. So we have 2x squared. And that leaves us with 1 plus 3 over 2x minus 1 over 2x squared. And on the denominator, we factor out an x. And that leaves us with 1 plus 1 over x. So when we do this, you'll notice that as we apply this limit, these terms are 0, same with this term. But when we cancel out our x's, we're left with an x on the numerator, which means this limit blows up. It doesn't exist. So there are no horizontal asymptotes. However, we're going to do something here. I am going to take this function and divide by this function. You guys remember long division? We're going to do that. So x plus 1, we're going to divide it into our 2x squared plus 3x minus 1. All right, let's go through some long division. We're in grade 12, but we're going to learn long division all over again here. So how many times can x go into 2x squared? Well, 2x times, right? Because 2x times x gives us 2x squared. But of course, this 2x we're going to times by the x to give us 2x squared. And we're going to times it by the 1 to give us plus 2x. Then we subtract. So 2x squared minus 2x squared cancels. 3x minus 2x just gives us x. And then we bring down the negative 1. And repeat. So what times x gives us x? Well, 1. So 1 times x gives us x. And then 1 times 1 gives us, well, 1. So when we subtract these, the x's go. Negative 1 minus positive 1 is negative 2. So what this function sort of can reduce to is I can rewrite it, f at x, as 2x plus 1, right, the 2x plus 1, minus this remainder of minus 2 over x plus 1. All right, so now what I'm going to do is I'm just going to draw a little sketch here. And let's say we had this line, 2x minus 1. So if I were to draw that line, it would look something like this. So this is y equals 2x minus 1. Right? And if I were to draw this whole function, well, at some point it would look, I'm not going to draw the whole function, but at some point around this point Q, where Q is the point x and 2x plus 1 minus 2 over x plus 1. So that's its coordinates. I can write that in there. So x and 2x plus 1 minus 2 over x plus 1. Now at the exact same x coordinate, we're going to have a value on y of 2x minus 1. So it's going to have the coordinate, let's call that p. And p is going to have the coordinates x and 2x minus 1. And what I want to figure out here is the vertical distance between p and q. So I can do that. So vertical distance between p and q is just their difference in their y coordinates. So I can write that as 2x minus 1. Subtract the y coordinate of q here, which is 2x plus 1 minus 2 over x plus 1. When I do that, well, 2x minus 1, plus 1. This should be plus. So 2x plus 1 minus 2x plus 1, well, those are just going to cancel. And I'm just left with this double negative here, which is 2 over x plus 1. And I want you to notice that if I take the limit of this, if I take the limit of the distance, the vertical distance between p and q, as that value of x approaches infinity, right, of that pq, you can look at this and you have a 2 over x plus 1. It's 0. So what does that mean? That means that this graph, the graph that we're trying to plot, is approaching this line but never touches it. That means it's an asymptote. So we just discovered the equation of our asymptote. The equation of our asymptote here is y equals 2x plus 1. And you can see that in the graph I have above, right here. There's our equation, the green line, y equals 2x plus 1. And you can see our graph approaches it from both sides, but of course never touches it.